Welcome back, everyone. In this video, I'll be continuing the section for the volumes of revolution. So in the last video, what we did was we looked at what a volume of revolution looks like. We derived a formula, and we talked about the formula we derived was really the direct formula for what was called the disk method. And the disk method was when our region that we're revolving, the entirety of the region's domain was touching the axis of revolution. Well, if that doesn't happen, like this picture here, you implement what is called the washer method. So when the area you are revolving around a particular line is not touching the line of revolution for the entire domain, so that's very important, you implement the washer method. And so this one here, I have a little section here. It looks sort of like a little ellipse or something. We have two curves, y equals f of x and y equals g of x. And this really here where the x value starts is our a, and where the x value ends is our b. Now, the only reason we use x instead of y, because we can use the y values to represent our domain, is because we're revolving around the x-axis. But as we'll see in the problem, if you revolve around the y-axis, you don't have to make too many adjustments. Okay. But this is the domain, because if we just look at the domain of the section, it goes from x value over here to x value over here, and it's not touching the entire way. This one, it seems to be touching it at one point, but that's not really important. The main thing is that it's not touching the axis of revolution the entire way. Right? Because it's not touching the entire way, that means our old method of the disk method directly doesn't work. But a pretty good indication that it might not work either is because that you have two functions, y equals f of x and y equals g of x. Now that's not a end all be all. It doesn't have to be two functions. You can still have just one function in the region that's describing, just does not touch it, the axis of revolution the entire way. So just be aware of that. But in a lot of cases, when you're given two functions and you look at the picture, it's going to look like the washer method. Right? Now, why is this called the washer method? It's called the washer method because when you rotate your little circles, or sorry, your little lines here to make the circles, make the small cylinders, it's not a filled in circle. It's going to be a circle with some space in between. So let me go ahead and show you a picture real quick. Once again, just kind of Google the picture so you can see it here. It actually has that same sort of shape, which is kind of funny. But what we have here, this is y equals x squared and y equals square root of x revolved around the x-axis. But the point here is you'll notice is that, actually I realized that it wasn't very big, but if you go ahead and look at it now, what's happening is over here you can see that when we revolve around it, it sort of looks like a donut. We have this open circle in between. And this can be, bigger or smaller. So when we're at the end here, the open circle is kind of bigger, but the point is that you have an open circle. So when you're finding the area of this thing, it's not just pi r squared because it needs to be filled in. What we have to do is we have to find the area of the bigger circle, subtract off the area of the smaller circle. And really all you have to do for that is, as you'll see, and we'll derive it very quickly, is that you're just taking the bigger radius squared minus the smaller radius squared. So you're figuring out what the bigger radius is, squaring that because that's the area of a circle, it has radius squared in it, and then subtracting off the smaller one. So you're taking the bigger area, subtracting off the smaller area. Now to make sense of this, just keep that picture in mind when I write this down. So let's say for the washer method, if the bigger radius is r with a subscript o of x, so its function is r o of x. The o is for outside. You can use really whatever you want. Some people just use r1 and r2, but I like o and I. And the smaller radius, that's how you spell radius, is ri of x. So I for inside, just meaning the closer one to your axis of revolution. So once again, for this one, Our RO, the outside one, would be the bigger one, so the part on this curve. And the RI would be the smaller one, this one on the inside, which is the inside curve. But for this specific example, just to put some labels to it, RO, the outside one, would be the square root of x, because this is the one that's farther away from the x-axis, or axis of revolution. And the RI, the inside one, would be the y equals x squared, because that's the inside. It's closer to our axis of revolution, the x-axis. Well, if you do that, if you represent them like this, then the area of the washer, or the donut, so just the circle with a circle cut out from it, is the bigger area, pi times r0 of x squared. So that's the area of the bigger one, pi r squared, minus the smaller one, pi ri of x squared. And just to make life a little easier, you can factor the pi out, and you get r0 of x squared minus ri of x squared. Well, all this does when it has the effect of it is when you want to find the volume using the washer method, we still do everything else the same, except that our area of the circle formula is not just pi r squared anymore, it's this. So we have pi times r0 of x squared minus, or sorry, ro of x squared minus ri of x squared dx. But the main thing to remember is that this is the outside, or the bigger radius, and this is the inside, or the smaller radius. Right. So when you draw the picture and you draw your axis of revolution, all you need to do is distinguish, okay, which one's outside or farther away, which one's closer, or the inside, and then you plug them in. After that, you're just doing an integral again. Right, so number one here, it says find the volume V of the solid obtained by rotating the region bounded by the curves x equals y and x equals y squared rotated about the x-axis. Now, like with the areas section we did in the previous section, you can or cannot be given the bounds. And if you're not given the bounds like this, that means that the curves intersect and you're just looking for that region. So before we worry about being rotated around the y-axis, we're just gonna graph these and see what does it look like. And that's always your starting point, is you should always graph your region, because otherwise it's pretty much impossible. So we want to graph x equals y, and we want to graph x equals y squared. And you can see the only region that's sort of stuck in between the two and enclosed is this one right here. So this is our region. Now, for the purposes of this problem, we do really need to pay attention to where they intersect, because we have to figure out our bounds from them. So I'm going to go ahead and make sure that we realize they intersect at 0, 0, and 1, 1, right? And this is y equals x squared, the red one, and this is x equals y squared is the red one, and x equals y is the black one there. So I'm going to go ahead and just draw this over here, keeping in mind where they intersect. All right, so let's go ahead and do that. So we have our xy axis here. The two curves intersect at the point 0, 0, and at the point 1, 1. So I'm going to go ahead and just circle those off for the intersection points. Now, x equals y was just the straight line. So pardon my ability to draw here, but that's x equals y. And then x equals y squared. It's the entire parabola that's sideways, so it looks completely like this, but we only care about the section where it's intersecting, so I'm just going to draw this part. All right, so here's the big thing. This one is being revolved around the y-axis, not the x-axis. So if I go ahead and highlight this, I only really care about the domain here. I can do the whole thing, but we're just looking at the y values. So think about smashing the region against the y-axis, and it's only this section. So this is our axis of revolution. What are the bounds? Well, because we're revolving around the y-axis, we want everything with y's. let's go ahead and just write that a little comment there. And in general, if you rotate around a vertical axis or a vertical line, so it doesn't have to be the y-axis, it could be like x equals 1. We could have revolved around this one, and we would just have to set up the problem slightly differently, but everything else would follow. So when you rotate around the vertical line, what you do is you use y for everything. Now it's exactly the same formula as above here. Instead of having x's though, you just have y's. And the main reason is because your formulas here, it's x equals and x equals. But it's going to be set up for you like that. So if you're rotating around the y-axis, you do at this point have to use everything with y's. And our formula should be x equals, and they are. So our bounds should be in terms of y. And they are, what's the smaller y value? Well, it starts at 0 and goes to 1. Now, these are coincidentally the same x bounds if we rotate around the x-axis, because x also goes from 0 to 1, so don't get confused there. We are rotating around the y-axis. So all we care about is the two bounds here. So this is the smaller bound at y equals 0, and this is the larger bound. Now, when we visualize rotating around the y-axis, what happens is this region comes back here. So we have the straight line, and then we also have, let me draw that a little bit better. I'm just trying to redraw this region. So we have the straight line, and then this, the part of the parabola here is inside. So we get this picture. And when we rotate around, you can sort of fill in the circles here. That's our bigger one, and this is our smaller one. And the shape you're left with is the disc between it. Or sorry, I want to say the disc, the washer. It's a circular shape, but definitely don't want to use the words that the other method uses. So it's this washer because it looks basically like a donut. You might prefer to even write the donut method, but it's just called the washer method. Right, so we have this picture here, and now the question is, how do we go about filling out everything else? Well, the main thing is that you still have the same formula. So you still want to do pi. You still want to do the formula for the outer radius squared. You still want to do the formula for the inner radius squared and subtract them. So go ahead and leave some space for that. And then instead of dx, you have dy because everything's in terms of y, but everything else is the same. All right, so what is the outer radius? What is the one that's farther away from our axis of revolution? It's x equals y. So x equals y is farther away. And what that means is that the RO, the outside radius of y though, be careful here because we're using y, but once again, it's just a replacement. RO of y equals y. Right, so this RO of y is really just like x, and we're just using the formula for x for that one. And then what's the inside radius? Well, it's just going to be the other one. We don't really have any other choices anyway, but Ri of y, remember that just really represents x, and this curve here has the formula y squared. But this one is the closer to the axis of revolution. Now it's important you think about it being the one closer to the axis of revolution and not any other way. If we were revolving around, let's say x equals 2 over here, then our smaller radius would be involving the x equals y because it would be closer to the vertical line over here. All right, but let's go ahead and plug them in. So RO of y is y, and then we want to square that, minus Ri of y, the inside one is already y squared, and then we square that. Maybe just to emphasize, I'll put that in parentheses. So this was the outer radius, this was the inner radius. But once you go through and do this, you actually have it all set up. Everything's y, dy. Some people like to take the pi in the formula and just leave it out front because you pretty much always factor it out. So I'm going to go ahead and do that. We have 0 to 1. And inside here, y squared minus y squared squared is y to the 4th. And we can go ahead and integrate this right away. We don't need any fancy substitution because these are just the power rules. So I'm going to go ahead and put my antiderivative in here. The integral of y squared is y cubed over 3 minus the integral of y to the 4th is y to the 5th over 5. Because it's a definite integral, we don't need a plus c, we just need from 0 to 1. And we didn't do any substitution, so we don't have to worry, did we forget to make a substitution back? Did we switch our bounds? Not relevant for our problem. And the nice thing is when you plug in 1 and 0, that's usually the most ideal thing. So when we plug in y equals 1, and we subtract y equals 0, that's usually the easiest numbers we can possibly plug in. When we plug in y equals 1, in the front you get 1 over 3 minus 1 over 5, because 1 to any power is 1. And when you plug in y equals 0, you can see pretty quickly, because it's powers of y, you just get 0. So we have pi times 1 over 3 minus 1 over 5. And now just get a common denominator here, and you can finish up. And 1 over 3, we multiply by 5 over 5. 1 over 5, we multiply by 3 over 3 to get our common denominator. And we finish it up, we got pi times 5 over 15 minus 3 over 15. And that is 2 over 15. So this is 2 pi over 15. Now, one thing I always like to point out here is the washer method is really the disk method doing two things. The our outer one, all it does is it would figure out if this whole circle wasn't here. All the our inner does, subtracting it off, is just said, oh, we actually have a space here, so we got to actually take that away. And that's all that does. So when it comes to using the washer or disk method, they are slightly different formulas because they have a different setup, but it really is the same type of formula. And the other point of emphasis I want to bring up in this problem is that we did not do anything special just because we rotated around the y-axis instead of the x. So keep that in mind. All we did was say, well, we have this formula. Technically, this is for revolving around the x-axis, or in more generality, a horizontal line. Whenever you rotate around a vertical line, you just use y for everything. Right, but in the next video, I'm going to show you how we do one if we're not revolving around just the x or just the y-axis. How do you make that adjustment? And you'll see, as long as you're careful, that it's not a big change. So I'll see you there.